Hi students, we are moving to third module, that is differential equations of higher order. In that first we are going to discuss about linear differential equation of second and higher order with constant coefficients. So you all know about that linear differential equation. What is linear differential equation? Any differential equation in which a dependent variable and its derivatives are of first degree is called a linear differential equation. So here we have a nth order linear differential equation, that is dn y by dxn plus a1 dn minus 1 y divided by dxn minus 1. It will goes on up to a n y, which is equal to y of x, where a1 a2 an are all constants. If we write d by dx, which is equal to capital D, likewise d square by dx square equal to capital D square, and d power n divided by dxn equal to capital Dn. Then the given differential equation will become d power n plus a1 d power n minus 1 plus up to an. Here y is a common factor, therefore we will keep it outside the bracket, which is equal to pi of x. So this term within the bracket is considered as f of d. Therefore, the above equation becomes f of d into y equal to pi of x. Here we have two cases. First one, if pi of x is equal to 0, then the above equation becomes f of d into y equal to 0. So this type of equation is called homogeneous equation. And second case is, if pi of x is not equal to 0, then the above equation becomes f of dy is not equal to 0, not equal to 0 or any function. Then the equation becomes non-homogeneous equation. Now we are going to find out or how to find the solution of homogeneous linear differential equation. Consider any second order differential equation, that is d square y by dx square plus a1 dy by dx plus a2y equal to 0, where a1 and a2 are constants. So if we take d by dx equal to capital D, then the above equation becomes d square plus a1d plus a2. Since y is common factor, we will keep it outside the bracket, which is equal to 0. By considering d square plus a1d plus a2 as f of d, the above equation becomes f of d into y equal to 0. Now, method of finding the complementary function. So we have f of d into y equal to 0, that is f of d is equal to d square plus a1d plus a2. If we put f of d, which is equal to f of m, then the above equation becomes auxiliary equation, that is f of m equal to m square plus a1m plus a2, which is equal to 0. This is an auxiliary equation. Since this is a quadratic equation, we have two roots for this equation. So depending on the characteristics of the roots, we have three cases or three types of solutions. First type, real and distinct. That means if m1 is not equal to m2, then the complementary solution will be given as yc is equal to c1 e power m1x plus c2 e power m2x. Second type, real and coincident, that means m1 equal to m2. Since m1 equal to m2, consider that as m. Therefore yc becomes c1 plus c2x e power mx. Now third case, that is complex pair. If m1 and m2 are complex pair of roots p plus or minus I cube, which is of the form p plus or minus I cube, then the complementary function becomes yc equal to e power px of c1 cos qx plus c2 sin qx. So this is a table of different type of roots and their corresponding complementary function. In first example, we have roots 2 and 3, that means real and distinct roots. Therefore the complementary function for those roots become c1 e power 2x plus c2 e power 3x. In third example, we have roots 3 and 3, that means real and coincident. Therefore the complementary function becomes c1 plus c2x e power 3x. In fourth example, we have 0, that is a real and distinct, and minus 2 are real and coincident roots. So here we have two cases. First one is real and distinct, and second one is real and coincident. So for 0, the complementary function becomes c1 e power 0x, and other three roots, so minus 2, we have the complementary function is c2 plus c3x plus c4x square e power minus 2x. By adding those, we will get c1 plus c2 plus c3x plus c4x square e power minus 2x. Fifth example is plus or minus 2i. So this is a complex roots. So plus or minus 2i can also be written as 0 plus or minus 2i. Here the value of p is 0 and value of q is 2. Therefore the complementary function becomes e power 0x of c1 cos 2x plus c2 sin 2x. Since e power 0x is 1, finally we get c1 cos 2x plus c2 sin 2x. So this is how we are going to find out the complementary function of any given homogeneous differential equation. So this is a problem given that d cube y by dx cube minus 2 into d square y by dx square plus 4 into dy by dx minus 8y equal to 0. So first we will write d by dx as capital D. Therefore the given equation becomes d cube y minus 2 d square y plus 4 dy minus 8y equal to 0. Since y is common factor, the equation becomes d cube minus 2d square plus 4d minus 8 of y equal to 0. So taking the term within the bracket as f of d, it will become f of d into y equal to 0. Therefore the auxiliary equation becomes m cube, considering d as m, okay, f of d equal to f of m. So therefore f of d becomes, or f of m becomes m cube minus 2m square plus 4m minus 8 equal to 0, So by taking m square common from first two terms, we'll get m square of m minus 2, and taking 4 as common factor from second two terms, we'll get 4 of m minus 2. Therefore it will become m minus 2 into m square plus 4 equal to 0. So from m minus 2 equal to 0, we will get m equal to 2, and from m square equal plus 4 equal to 0, we will get m equal to plus or minus 2i. Therefore the roots of the auxiliary equations are, first one is 2 and second is plus or minus 2i. Here 2 is a real and distinct root and plus or minus 2i is a complex root. Therefore the complementary function becomes, for first root 2 we have c1 e power 2x, for second root plus or minus 2i. Here value of p is 0 and value of q is 2. Therefore that will become c2 cos 2x plus c3 sin 2x. For the complementary function is c1 e power 2x plus c2 cos 2x plus c3 sin 2x. Now second problem, given that d cube minus 3d plus 2 of y equal to 0. So the given problem is already in the form of f of d into y equal to 0. For this equation we have auxiliary equation is m cube minus 3m plus 2 equal to 0. Writing f of d which is equal to f of m, we will get auxiliary equation. So this equation cannot be factorized. Therefore by using inspection method we will find one root. So by putting m equal to 1, the equation becomes 0. Therefore 1 is a root. So using that root, that is 1, and also by synthetic division we will find the other roots. So this is how we are going to find out the roots by synthetic division. So first write the coefficients of all the terms in auxiliary equations. So coefficient of m cube is 1, and here we don't have m square, therefore we take the coefficient of m square as 0. And next term is m, the coefficient of m is minus 3, and the constant term, that is 2. We already got a root, that is 1, so write it left side and make a table like this. So always we have to put 0 below the first term, that is 1. Here we have first term 1, so below that we will write 0. So adding those terms, that means 1 plus 0 becomes 1. So this result 1 should be multiplied with the multiplier, that is the earlier root 1. So 1 into 1 becomes 1 again. So write that below the next term. So we are going to put 1 below the term 0. So adding these terms, 1 plus 0 becomes again 1. So again multiply 1 with 1, we will get 1. So write that below the next term. So here we have the next term is minus 3, below that we will write 1. So adding these terms, minus 3 plus 1 becomes minus 2. So again multiply minus 2 with 1. So minus 2 into 1 becomes minus 2. Write that below the next term, that is 2. So 2 and minus 2, by adding these terms we will get 0. Now we have to write this in terms of a quadratic equation or in equation form. So last term is 0. By neglecting that, first from right side, first we have minus 2, so taking that as constant. Next the we have 1, so that is coefficient of m, and again we have 1, that is coefficient of m square. Therefore we will get the equation m square plus m minus 2 equal to 0. By solving this equation we will get the roots minus 2 and 1. Initially we have got a root, first root, that is 1. Here we have two roots, that is minus 2 and 1. Therefore we have finally three roots, minus 2, 1, 1. So here 1 and 1 are real and repeated roots, minus 2 is real and distinct root. Therefore the complementary function becomes c1 e power minus 2x plus c2 plus c3x of e power x.